Hi! Taboo Conspiracy uploaded a video yesterday, and this one is a bit unusual for a flat earth video because it actually presents some maths. It's supposed to be maths for how perspective changes the size of things, but it has a few, well, let's say shortcomings. Mr. 42 already did a nice video on the topic, and I'll link it in the description. Here's a fragment with him getting to the part with the calculations.
Sorry, you're doing what now?
Now, my initial reaction was about the same, but if you think about it for a while, there is a method to this madness. And by this I mean these are not random calculations, they actually serve a purpose, although the utility of this purpose is questionable to say the least. Now, let's take a look at what the calculation is. Taboo Conspiracy calculates what he calls apparent height, which depends on the observer height, the object height, and the distance to the object. He doesn't define what it is explicitly, but we can take his calculation to be the definition. So, to calculate it, we take the distance to the horizon, which depends on the observer height, and the angular size the object would have at this distance. Then we divide the actual angular size of the object by it, and multiply the result by the object height. Tada! That's it. Looks a bit convoluted, but it actually has a simple interpretation. If we draw the same object, like for example a mountain, at two distances, once at the distance to the horizon and the other time at the actual distance, then the angular size of the object at the horizon here will be represented by the angle between the red lines, and the actual angular size will be represented by the angle between the blue lines. Then the ratio of angular sizes is roughly the proportion of the length of the blue line segment here to the whole height of the object, which is the red line segment in this illustration. Then the apparent height is just the height of this blue line segment. Or to put it differently, apparent height is the height of an object at the horizon that would have the same angular size as the target object at the given distance. Well, approximately, because angular size isn't exactly proportional to the linear size, there is some trig involved, but it works well in most cases. Why would anyone want to calculate the equivalent height for an object at the horizon, and what does it have to do with perspective, is something only Taboo Conspiracy knows. Nevertheless, there are two major problems here. The first problem is the distance to the horizon is a crucial part of the equation, and that is a globe calculation. You're gonna need r for that. The second one is slightly less obvious but also quite easy to see. If the apparent height of objects further than the horizon is less than their actual height, what happens to the apparent height of objects closer than the horizon? Let's take a 1 meter stick as an example. If the observer height is 2 meters, the distance to the horizon is 5 kilometers. And I'm just looking at the geometric horizon right now, so 5.05 kilometers. At this distance, the angular size of the stick is roughly 0.01 degrees. At the distance of 1 meter from the observer, the angular size is 53.13 degrees. So let's put that into Taboo Conspiracy's formula, and we get that the apparent height of a 1 meter stick that is 1 meter from the observer at height of 2 meters is almost 5 kilometers, 4.682 to be precise. And it actually gets better. The whole video from Taboo Conspiracy was about Mountain Denali, so let's see what happens if the observer is on top of Denali. The height is 6,190 meters in such a case, and the horizon from this distance, again the geometric horizon, is 280.91 kilometers away. The angular size of the stick at this distance is 2.0396 e minus 4 degrees, which is 2 parts in 10,000. So if the observer is on top of Denali and looks at a 1 meter stick from the distance of 1 meter, the apparent height of the stick comes down to over 260 kilometers. I'm sure this makes some sense. After all, Flatzoid has been trying to explain this to us for years now. Other prominent flat earthers also seem to agree that this video is brilliant. So I'm sure that 1 meter stick on top of Denali having an apparent height of 260 kilometers is reasonable, and I just don't see it. If anyone can enlighten me, I'll be deeply grateful. To stress his point, Taboo Conspiracy released a supplement in which he presents two observations, so I'll address this quickly. Over to him.
Example 1. If a camera is placed at 2.25 feet above the water and is filming a boat approximately 6 to 7 miles away, would a bird and rock about 1.25 feet above the water ever be taller than the distant boat as portrayed in this diagram? Does this orthographic view generally represent reality?
So if the camera was above the bird and the rock, no, it wouldn't. So I agree with him here.
Here's the actual footage from Wide Awake. Is that a giant bird on a huge boulder?
And is the camera above the bird and the boulder here? Because I doubt it. So let's look at the horizon. From this height above the sea, the horizon is almost exactly at eye level, and it cuts the rock in half, which means that the bird is higher than the eye level, and the situation in this observation is much different from the one that was presented in the orthographic view. So no magical apparent height needed here. The second example is with a ladybug in front of some other objects. Again, the claim is that the camera was higher than the ladybug, so this shouldn't happen. Here I simply don't have enough data to say what exactly happened. Maybe the camera was something like a phone camera and really low above the floor. Or maybe the floor wasn't perfectly flat, because they rarely are actually. Or maybe the ladybug's apparent height was measured in kilometers because of Taboo Conspiracy's math. Who knows? Anyway, that's it for today. Thank you and see you in the next video. Bye!